Welcome back. The next speaker is Viv, and she's going to talk about finding spin glass around the states.
The fourth talk, and I've hopefully done enough background now that what I'm going to present is going to have a good context for why it's both interesting and useful in many senses. So here's the overview of the week. We've got our computational context. We've seen how we can do computing with quantum walks in many different ways. And we've looked quite hard at the search algorithm in the context of an optimization problem. There are other ways to do search with quantum walks, and I expect there'll be more on that from Renato's talk this afternoon. So today I'm going to pick up the quantum walk doing optimization problems theme and look at finding spin glass ground states. So this is our computational context. We have a quantum computer here, a quantum system, and we have a problem we'd like to input, encode it into our quantum system, run some dynamics, decode it, and get our result. And the dynamics we want to run it in continuous time. So we're going to do continuous time quantum walks. So this is the picture that I established in the previous talk using search algorithms. So for optimization problems in general, search being a special case, the Hamiltonians that are used for that continuous time evolution are essentially the same with some different time-dependent controls on how much of each component that you use. So we have our quantum walks over here as one corner. An adiabatic quantum computing is a different type of unitary time evolution, but you can interpolate smoothly between the two, and you can use hybrid versions that have characteristics from each. And then I will not be covering in this set of this mini course, but just for the background, if you want to do real quantum computers, you're going to have real physical systems, and having perfect unitary operations is near impossible. So they tend to sit somewhere over here where you've got some open system effects. You're actively cooling the system to bring it closer to quantum ground states. And you also get noise you don't want, which you can think of as out of the plane at higher temperature. And all of this is a sensible thing to do. It exploits natural properties of quantum systems, where you can smoothly do a transition from 0 to 1, and you can stop anywhere in between in the superposition. You can't do this with classical bits, then the way they're defined. They have two discrete values, and that's it. You can flip between them. So just a cartoon picture of that open system version. It's like doing adiabatic quantum computing, but running it much faster, and a low temperature bath to help removing the energy to reach the ground state. However, all this interaction with the environment may kill the helpful coherences, which are the part of the quantumness that does the computation efficiently. Mm-hmm. And just note that if you're reading the literature, these terms are often used interchangeably. It'll be called quantum annealing when they're studying adiabatic quantum computing, and vice versa. So it can be confusing. You check what they're actually doing. So this is a cartoon of what we're doing in that open system, and a motivation for why hybrid algorithms, and considering classical as well, and even the fact that you lose some of the quantumness might be helpful. This is a cartoon energy landscape. So we have broad energy minima, and we have lots of narrow ones. Now, quantum states get stuck in broad minima like this with wide barriers, and don't have a better way to get through to the true minimum any more than classical states do, but classical states, so to jump like this, you can just as well do classically. But once you're in a where you've got narrow barriers between different false and true minimum, then quantum systems can tunnel. So they can get through barriers without having to have the energy to jump over the top. And that's why they win, and one of the reasons why they win. So that's enough about that as an aside, as to why this is seen as a practical way to build a quantum computer, not just a piece of theory. So this we saw yesterday. This is continuous time quantum search. So the quantum walk is here. If you look at the graph up this line on this axis, you can see nice sinusoidal oscillations that give you maximum finding the mark state perfectly. This is all in the large size limit. And then adiabatic quantum computing is over here, and it takes a little longer, and it only reaches probability 1 asymptotically. So in this ideal setting, quantum walks are your best choice in this continuous time range. And it's also, for encoding, I explained why we want to use hypercube graphs in Hilbert space. So I wanted, just before we come to the spin glass problem, again emphasize that we have two kinds of graphs here. We have the qubits that we're going to encode our quantum walk computation in. So here, corresponding to it, we have the Hilbert space and the allowed transitions within Hilbert space that are given by this Hamiltonian here. And you can see I've got some little dotted red lines between the qubits. So they're interactions between the qubits that we use to define the problem Hamiltonian. So in real space, in qubit space, if you like, there's a graph that represents the problem, how the interactions are set up between the qubits in order to define the problem we want to solve. And then over in Hilbert space, there is a graph that is a dynamic graph, if you like. It's the graph on which the dynamics occur, and that's given by the Hamiltonian. This is a Hamiltonian for walk, quantum walk on this graph. When you turn that into a matrix, this piece gives you the adjacency matrix of a hypercube. So there are two graphs. They're independent at some level. The size matches with n and 2 to the n. But apart from that, you can choose them independently. You can set your problem up independent of the graph then that you use to do the dynamics to find the solution. And you very often might put a complete graph here instead. That will then have different operators here, but it's analytically easier to solve. The hypercube is challenging, but analytically solvable in many aspects. We had a bunch of caveats we found after looking at quantum search yesterday. This is just a repeat of the slide. You need exponential precision for the hopping rate for the parameters in order to get the quadratic speed up. And if you want to really do encoding the mark state into a hardware that only has pairwise interactions, you're going to need to use extra qubits, and you can do it unless you want to use exponentially many qubits, you'll have to do it perturbatively. So it's a great problem for theory, for analytical solutions, the classical simulation, and you can implement it with these extra qubits if you know the answer in advance. So it's a good testbed problem, but it's not similar. In many ways, it's really not similar to real world problems that we might really want to use a quantum computer for. So it's time to look at something that has properties that are much more like the kind of optimization problems that you might want to solve for real. And the one we chose to look at first is Sherrington-Kirkpatrick spin glasses. So these are two physicists, theoretical physicists, who defined this model. It's actually a classical model, and they defined it to model magnetism, and back in the 70s, 80s. So it's theoretical condensed matter physicists have studied this model in a lot of detail. A lot is known about the phase transitions and phase diagram for this kind of system. Essentially, it's a frustrated spin system, and I will explain frustration on a slide in a slide or two's time. So what you're doing, what you've got is a whole set of qubits, two-state systems that interact, and you want to find the ground state, the lowest energy arrangement of the zeros and ones. It's NP hard for finding the ground state, so you expect a polynomial speed up, not exponential. And it has many characteristics that are more like hard optimization problems. So I'll give you the definitions properly on the next slide. We chose it because it had already been looked at by others for how well adiabatic quantum computing can find the ground states. And they can find them faster than guessing, which is the best you can do classically. In a naive sense, there are better algorithms for doing this. I'll discuss this once I've discussed what quantum walks can do. And so this is the equation. We now have time dependent. So here's the Hamiltonian that does the quantum walk. And here's the problem Hamiltonian. And then we change the proportions of each if we want to do adiabatic quantum computing. Now, at this point, I should make a couple of notes about history here. So it seems obvious that now that if you have something adiabatic quantum computing works on, we should see whether it also works for a quantum walk. So same Hamiltonian, different time dependence. But even though back in the late 90s, early 2000, some of the same people came up with quantum walk computation for continuous time and adiabatic quantum computing, they didn't put them together like this and think of them as something you could interpolate between. To my knowledge, the first time this was done is the work that I showed you yesterday from 2018-19. In fact, Sugato, Boza, and I started looking at this about 2012-13, and it took quite a long while to work through all the details and see how it would actually work out for the search problem. So there are algorithms for quantum walks, there are adiabatic quantum computing algorithms, but the connection between them is much more recent. So at the time we started this work, to try to use a quantum walk to find the ground state of a spin glass was not a type of problem that anyone had tried to apply a quantum walk to before. Let's see how it works out. So here's some definitions first. So Sherrington-Kirkpatrick spin glasses, as I said, frustrated spin systems, and they're a model for magnetic materials. So spins are, and I should in principle start out by doing classical spins, because this is in fact a classical model. They're two-state systems, spin up or spin down, depending on whether neighboring spins are aligned, both up or both down, or anti-aligned, they have a different energy. So here's the Hamiltonian that I wrote, and I've written it already quantum with quantum operators. But if these were just classical spin values of up or down, the up value can be +1, the down value can be -1, but encoding is arbitrary, so I could switch the plus and -1s around, I could use different values, and it would have the same properties. Now, also, and I have not used this in previous talks, but I've just put it here for completeness, a Hamiltonian is an energy function, so it has units. It has the units of energy, and these are numbers, and these are operators that don't have any units, and they act on quantum states that also don't have any units. So you need something with units, some energy that makes the whole equation make sense from a physics point of view. And I've put it over here instead of there, because without loss of generality, I can set these factors that have got energies, units, to 1, and they don't make any more difference to the outcome from the point of view of looking at the results. Everything is just scaled by something that has the right units, depending on what you're doing. And I've already left my h bars out. Again, I'm working in units in which h bar has the value 1, and it doesn't change the maths that goes on. Define our spin glasses by drawing these constants here from a Gaussian distribution, and we choose it to have mean 0, which makes the problem harder. There'll be some standard deviation for this Gaussian distribution. Again, that becomes a prefactor that we can set to 1 without loss of generality. And this is the original definition. I could have just drawn one number here. It very slightly changes the statistics when you average like this, but again, not in any significant way as far as we're concerned. This problem, to find the lowest energy state of this Hamiltonian that this Hamiltonian induces in the spins, it's NP hard. That so that basically means that's why, as I said, we don't expect an exponential speed up for solving this in a quantum way, but we would expect instead a polynomial speed up like search. So maybe quadratic, we would expect us to be able to do that. The quantum walk Hamiltonian on the hypercube. Here it is again with the technically correct energy scaling omega. We combine it here with our hopping rate, which is the parameter we get to vary in order to optimize the performance of the algorithm. When you put these two things together, then it becomes quantum. It becomes a transverse Ising Hamiltonian. This is just an Ising Hamiltonian. This is the transverse field. And the fact that these operators don't commute is why we get quantum in this setting. Now, these Ising Hamiltonians, if you turn that into a matrix, it will be diagonal because the Z operators are all diagonal. And so what you'll have down the diagonal of that matrix will be the eigenvalues in some order, depending on what order you've labeled your spins. Ising Hamiltonians are universal for classical problems, and we can build them easily. Remember, this is a model for magnetic materials. It's two-state systems with nearest neighbor interaction or neighboring interactions, and we can make things like this in the lab. So it's interesting for solving classical problems. We can't encode a quantum problem into a Hamiltonian that is essentially classical. If we added extra terms here, say YY terms, then we could put quantum problems in here, but they're harder to build then. So let's stick to this setting because many, if not most of the problems we use computers for are in the optimization setting are classical problems anyway. So frustration. I promised you I'd explain frustration to those that don't know this as a concept or term. This is what you get in antiferromagnetic spin systems. where you have a lower energy if the spins are anti-aligned. So we have two spins like this or like this, compared to if they're aligned like this or like this. So that will have higher energy than this. So here are three spins, the simplest example where this happens. And so if we look at these two spins, they're anti-aligned, and so we can assign them energy -1. If we look at these two, they're anti-aligned, so they also have energy -1. But then we don't have a choice about this. If they're anti-aligned, these two are going to end up aligned. So now we have energy +1. So the total energy here is the sum of these energies. And so we end up with an energy of -1, not -3, if we could set all of these individual links to the lowest possible. So that is without these J factors and H factors here. All I've done here is shown you what the Pauli Z operators are doing to these spins to give you the energy of individual ones and of a pair like this. So with the label here, the J will only act on the first spin and the K will only act on the second spin. So we have some fields that bias some of our spins, and then we have these interactions which correspond here. So we have weights at the vertices and weights on the edges that are given by our Gaussian random variables. And these can be signed ± or -1. So it can invert the frustration relationship for particular vertices or interactions. So if you have a whole lot of them, as written here, every spin in the system interacts with every other. So the interaction graph between the qubits is the complete graph, but it's a weighted complete graph. And what we're looking for is the assignment of spin up and spin down that gives the lowest energy out of this Hamiltonian. You can see why this problem is going to be hard. We don't know what the lowest energy will be. It depends how many of these interactions we can satisfy and what the weights are from these coefficients here. Now I'm going to compare the spin glass with a problem that is, and remember the spin glass we chose because we know adiabatic quantum computing can do something promising with it, solve finding the ground states. I'm going to compare them with a problem that we know is hard for adiabatic quantum computing. So it was defined by Eddie Fahy and collaborators in 2011. It's a random energy model. So it's, again, a simple spin problem. Instead of picking the coefficients here from a Gaussian distribution, now we just directly pick the eigenenergies. So we don't think about the interaction graph and the values of the J's or the H's that specify the weights. We just, for a set of n spins, we draw values from a Gaussian distribution with mean 0, and we need 2 to the n of them, because when we tensor up for n two-state systems, we'll have a 2 to the n by 2 to the n matrix. And down the diagonal, there will be the eigenenergies in whatever order they came out from the Gaussian distribution. So I've labeled them A, B, C, because we don't know which is E0, which is the lowest energy now. They're not ordered in that sense. They're not ordered by value. So our Hamiltonian for the random energy model is just the diagonal matrix that has these eigenenergies down it. So it's kind of like a search problem, but you don't know when you find the solution. You can check the energy. You can easily put the spin assignments into the Hamiltonian and check which one of these it is. But in order to know which one's the smallest, you're going to have to look at all of them. So it's a hard search problem. And the reason it's hard for adiabatic quantum computing is because now you don't know where the minimum energy gap is, where you need to slow down like you need to for search. If we're going to apply a quantum walk to the spin glasses and the random energy model, we need to choose our hopping rate. This is the only parameter we've got to play with, the relative weight of the two components, the driver and the problem Hamiltonian. So what we did first numerically is we tested, this is 11 qubit examples, so n is 11. We checked what happens for different hopping rates. And for the spin glasses, we found these nice bumpy broad peaks that mostly overlap for different instances. Like these are 3, but we tested 10,000. And what we're comparing here is the long time probability of finding the ground state. So the values here are quite small, but I'll deal with that later. And the reason we were using this is because you can calculate this from, if you can find the eigensystem for the Hamiltonian, then it's easy to calculate it's like the limiting distribution or stationary state, and we just need that for the one node of the hypercube that happens to have the lowest energy. And here are these omegas turning up so that everything has got units where it should do, and not where it shouldn't. Now, if we do the same thing, try a range of gammas for the random energy model, you get quite different graphs. You get sharp peaks, and they don't overlap completely. So if you happened to be here, you do really well for this example, and you do really badly for the other two. It looks like you're doing better for the random energy model because the probabilities here are higher compared to these. That's 0.05 and that's 0.05. So even if you're somewhere down here, you're still doing as well as the best spin glass. However, what I haven't told you is how long it takes you have to run, because a long time success probability is fine, but we're not going to run forever until we've worked that out. That won't give us an advantage. So we need to know what the run times are. But before we do that, from this, you can pick out an optimal gamma, wherever the peak is for any given instance. So you can take an instance and assign it the gamma that does the best possible probability based on the long time average, the limiting distribution. And that's fine, but you can't do this in practice, not for a real problem. This is the equivalent of solving the problem before you start. So we need a heuristic. We need a way to set the hopping rate that doesn't depend on actually solving the problem classically before we apply the quantum computer, because that's cheating, basically. And for the random energy model, we need the hopping rate to be precise if it's going to work. But as we can see here with these broad peaks, we're not going to need that for spin glasses. So what we're going to use is the average energy spread for each part of the Hamiltonian. Because knowing what works for search, you basically need to balance these so that they are roughly the same size. And you choose the gamma so that the energy of each piece is close to the same. So we're going to average the maximum and the minimum eigenvalues, eigenenergies. For the driver Hamiltonian, or gamma times it, that is easy to work out. It's 2n. Now, I think I showed you a slide for the search that had the eigenenergies for this Hamiltonian, where the spread was n, not 2n. Now, there's always a factor of 2 floating around the definitions of the hypercube Hamiltonian, and it's in different places in different publications. And I think that the factor of 2 has just popped up here as part of the definitions. It's not that I have a mismatch in what was worked out between the two. For the same thing, averaging the energy spread for the spin glasses, we're going to approximate it by using a Gaussian distribution. So it's not exactly a Gaussian distribution. Now, the random energy model it is, and this will give us exactly what this is, what the average energy spread is. But for the spin glasses, the tails are not Gaussian, and that's important. However, to approximately give us a value for gamma, so that's the inverse error function for the size, so 2 to the little n, the size of the problem we're dealing with. So that tells you what the likely largest and smallest are if we've taken n samples. The standard deviation of the distribution, so that approximately Gaussian distribution that we're working with. This is something that we can calculate from the definitions of our spin glass. And it turns out numerically that there is a prefactor correction of about 0.88. So it's close, but those tails slightly mess you up. So what we've done in the numerics is we've included that prefactor correction because it's something that you will be able to estimate for real problems. You equate these two, solve for a heuristic gamma, and then that means we're using the same heuristic gamma for all of our instances. We're not doing individual ones for different instances. And so that's going to be okay here. It's not going to go so well for the random energy model. And indeed, that's what you see. So if we use the optimal gamma and we look at the average long time success probability, the optimal one is here, and the heuristic one is a little lower, and it's scaling very, excuse me, it's scaling a little bit worse, but only by about 1 or 2%. So this is what it looks like for the random energy model. If you've got the optimal gamma, you've got this odd behavior as it dips and rises again. But if you have the heuristic gamma, it's falling. Pull back a slide from yesterday where we looked at finite size effects in quantum walk search. What I've got here is 5 to 11 qubits. So if we look at 5 to 11 here, we've got something that does something very similar. It's just a bit compressed on this graph because I've got a lot more sizes on there. So basically what we're looking at here is a piece of finite size effects of the random energy model. And what we've got here is what I told you but didn't show in graph form yesterday, is that if you don't have the exact hopping rate, your probability just falls off as the size increases. Right? We've got a heuristic hopping rate that is going to work well for spin glasses. This doesn't work for the random energy model, so we'll keep using the optimal hopping rate so that we can make some comparisons later for that. So now we want to look at dynamics, because it still looked here as though the probabilities are higher for the random energy model, indeed they are, than the spin glasses, but we've only looked at long time values here. And what we need are run times that are going to be realistic if we're going to get any kind of advantage. So let's run a quantum walk on a spin glass. So here we are for 40 time units. The time units are determined by our energy units. And what we've got is something very spiky, oscillating around relatively low probabilities here. This is an 8 qubit example. So this is no good for determining what time to measure, because it's far too many oscillations, and we've no idea how to catch one of these peaks. There's no way to calculate that measurement time. So what we do instead is we measure at random times in order to sample from the time average probability distribution. And so this is the instantaneous probability. And if we integrate that from t to t plus delta t, divide by delta t, we've averaged over that slice, say from 10 to 20, if delta t is 10. And if we do that, if we take this as and do it from 0 to a lot, relatively not, whatever value we're at, then this is the time average. And you can see it asymptotes quite quickly to a steady value that is somewhere in here for this example. And you can see that it converges very quickly. So we don't have to wait very long before we're going to be sampling from a distribution that has a mean that is here. So operationally, we can do this. We sample for repeat the run sample for a bunch of different times. And those samples, the average of those will the probability will converge to this probability of measuring the ground, of finding the ground state. So the scaling of this convergence time, which I won't show you the graphs for, is very fast, as I said. It's of order log n. Numerically, we find that the scaling is even a little better than that. It's 0.75. So little n is log of big N. And energy model dynamics are much, much slower. So look here. And so this was 0 to 40. And this is 0 to 200. So 40 is about here. And so you see, we can do the same thing at a time average, but we have to run it for much longer in order for it to converge to the time average. And so now, even though the probability is higher, we have to run for much longer in order to get not to be sampling. If we ran it for, say, 5 units, here we would be converging nicely to the time average. But here, if we ran it for 5 units, we would have a very low probability. So that's where the dynamics between the two, the difference between it matters a lot. Here now are some results that are using the spin glasses only for the minute. We're using the heuristic gamma based on the energy scales. And we have calculated the infinite time average for the blue dots. And then when we get to 13, we run out of computational power to diagonalize the matrix. It's 2 to the 13 by 2 to the 13, remember? And so then we've done a short simulation that is just delta t is 5, and we've started at 12.5 units. So, and we've done that for all of them. And what this is showing you is that this choice of parameters here is converged almost perfectly to the long time average. And then we've run it for the ones we couldn't do the long time average for, and that fit carries on beautifully. And what we get is a scaling that's about minus 0.41. So how to interpret that? If we had a square root scaling, which is what we would get for search, that would be minus 0.5. And if we were random guessing, it would be minus 1. So what we're doing here is we've got a scaling that's better than we would do if we just did a search algorithm. And we didn't need to solve the problem to set our parameters. Our heuristic is doing extremely well here. So why are we beating search? We're doing this because there are correlations in the problem, and because we've matched our driver to the correlations. So our spin glass Hamiltonian, or any other problem we've encoded into this, has pairwise correlations in there. The strength of them is given by these randomly chosen J terms. And we've got a driver that does single spin flips. So if you've got one of these that's got to spin up, so it's got high energy, a spin flip is enough to make it low energy. So what you want to do, if you've got pairwise correlations, is single spin flips, and that's what we put together here. And to demonstrate this, what we've done is done several other data sets or modifications of data sets. So first of all, we removed these pairwise correlations from the spin glass data in two ways. First of all, what we did is we scrambled the eigen. So we took the diagonal matrix and we scrambled the entries along the diagonal. So now they're random. They don't correspond to these pairwise terms anymore. And we still ran it with the single spin flips. And so that gives you the one over here. And that, remember, that's the shape you get from the random energy model. So it's now gone to the same shape as the random energy model, finite size effects, with the exact gamma. We're using the optimal gamma here. Then we, instead of using this driver, we use the complete graph driver. So that's the yellow one here. And again, the driver doesn't match the pairwise correlations. Well, now we can flip any number of spins at once. It's equally likely we'll fit 5 spins as flipping 1. And again, we lose that nice scaling and we get something that looks like the random energy model or search. But then we took the random energy model and we added some correlations. Now, we did this in quite a rough and ready way. It doesn't make a hard problem. We took the energies that are those energies randomly placed down the diagonal for the random energy model. We sorted them and we assigned them to a gray code. Now, a gray code is an ordering of the bit strings, the binary strings from 0 to n-1, where instead of it being ordered in what you're used to for counting in binary, they're ordered so that there's between any given one, you only need to flip 1 bit. In other words, energies that are close in value now are just 1 bit flip away from each other. So as I say, it doesn't make it a hard to solve problem classically. There are other ways to solve it, but it does give us pairwise correlations with exactly the same random energies as we had in the random energy model. We've just reordered them down the diagonal, where the bit strings now index energies that are close in value. And when you do that, and you use the hypercube driver, it now produces a scaling that is straight, that is not unlike the spin glasses. So what we've done is we've shown that it's both of these matched together that give you the nice scaling and the good behavior with the broad peaks for choose, so you can use a heuristic value for the hopping rate. You don't need to know it precisely. And we've done that by removing them in 2 ways, removing them either here, or by putting them in to what was otherwise a random energy model. So this is kind of important now to understand how to see the link between how we're setting up the problem and the weighted graph terms here, and then the graph that you use over here in order to drive the dynamics of the quantum walk. So that all sounds wonderful. We've got an algorithm better than search, using quantum walks, and on a problem that people had not thought quantum walks could solve. However, it's not quite that simple. It never is. Now we better deal with how good is the best classical algorithm. And it turns out here, here is my optimal gamma line. Here is my heuristic gamma line. So it corresponds exactly to this line here. That blue one there is now this one. And here is the best known classical algorithm. Best known, not a proof it's the best. And you can see this, here is 0.41, 0.4, and sorry, I got the heuristic is the purple is this one, and the optimal is this one. So now this one, the best known classical is 0.37. So it's better than we're finding with the quantum walks. So this is a branch and bound algorithm. It's been known for many decades, since the 1980s, for solving many different problems of this type. And Ashley Montanaro at Bristol took this branch and bound algorithm, put a quantum search subroutine into it, and got square root of that. So got about 0.18, which I haven't drawn on here. It's somewhere below this one. So we have some rather impressively good alternative classical and hybrid classical quantum algorithms. So we went, okay, let's do something hybrid between adiabatic and quantum walk. And so this was our first attempt. We just put a little piece of pre-annealing, like a short piece of running adiabatic fast before we did our quantum walk. And if we did that in a relatively naive way, what we get is now something like 0.28 or so, so better than classical now, not better than the square root of this, which is the branch and bound augmented algorithm. Then we did some optimizing of this, which is definitely cheating. We would not be able to determine these parameters efficiently for real problems, but we wanted to see how good we could get. And now we're below even the square root of this. But these are not proven to be a speed up that you could actually get in practice. We just wanted to try to find an upper bound on what we could do. And we don't know how badly we've cheated. So at this point, this stuff doesn't appear in this paper because it was just work in progress, and we don't at this stage have more rigorous results for how well you can do when you do hybrid algorithms. So we're now reaching the summary. I hope I've demonstrated that, at least numerically, and there is potential for analytical results here, because there are many analytical results for different types of spin glasses and spin systems. But it's not my expertise. There are many more expert people out there who could potentially turn some of this into analytical, more scaling results. And I hope I've shown you that quantum walks can work on a whole class of problems that people had not tried to apply them to before in the optimization setting. We've got a quantum speed up that beats search, but it doesn't beat the best classical yet. That would require more work. But the key thing here is that the correlations are what is making this work. So if we tried to do this with the complete graph, we'd have got a result that looked like search, and nobody would have been surprised, because you could apply search to this problem and get a square root speed up, and indeed apply it to the branch and bound algorithm and get a square root speed up. So in graph terms, we're choosing a hypercube to go with the Ising Hamiltonian. And that leaves us an open question. If you have a different choice of problem Hamiltonian, not just pairwise. Suppose you have more complicated graph with where you link more nodes at once. What would you choose for your driver Hamiltonian? What graph would go with that? And finally, to note that again, for these small problem sizes we're looking at, we need hybrid strategies in order to get a really robust quantum speedup. So here's my overview of where we are in the talks. Tomorrow I will look back and pull some of the questions and points that I didn't cover as I gave the basics between search and spin glasses, and I will look at another problem that quantum walks can solve, from which we can learn more about what's going on with these small size problems and the potential for solving larger instances. So thank you very much.
Thank you, Viv. Are there any questions? So let's thank Viv again.